Well, hello, physical science class. Hope you guys are all doing okay and staying safe during this ongoing social distancing time. Definitely miss not being able to see you in class. I've had to actually change venues to my house. My wife got called off to a birth, so we're going to do the very best we can. I've got 5 kids here in the house, so if it gets a little bit loud at some point, I apologize in advance. They've been told to try to be quiet while I walk through this lesson with you guys. So we're going to be looking at 17C and D today. We're looking, first of all, at classes of elements. Now remember that all of both physical science and physics and chemistry reminds us that God has created a very orderly universe. So we're not all that surprised to find order in creation and commands in Scripture governing how the church is to be ordered as well. 1 Corinthians 14:33 says, "For God is not a God of confusion, but of peace, as in all the churches of the saints." So God, who has ordered a orderly creation, has also provided order and direction to the church. And we even see order in government and all of the rest. God has provided order within society. It flows from a God of order. And then we see that same sort of order within the created universe. Now, last week I kind of challenged you to see if you could memorize at least the first 10 elements of the periodic table. And then I said maybe at the end, even if you wanted to try to memorize the first 20, that'd be even the further challenge. I gave you a little story to try to remember them. I'm going to see if you can remember them right now. So why don't you try to say them in order, and I'll pause in between each one, see if you can think of. What's the first one? That's right, hydrogen. What's the second? Helium. The third? Lithium. The fourth? Beryllium. The fifth? Boron. The sixth? Carbon. The seventh? Nitrogen. The eighth? Oxygen. The ninth? Fluorine. The 10th? Neon. Now, if you went even further, can you do the next 10? See how well you do. Number 11? Sodium. 12? Magnesium. 13? Aluminum. 14? Silicon. 15? Phosphorus. 16? Sulfur. 17? Chlorine. 18? Argon. 19? Potassium. And 20? Calcium. Well, if you did all the first 20, that's pretty impressive. I'd like for you to at least memorize those first 10, all right? So here is the periodic table. But no, this is a slightly different picture than you're probably used to. Here's a picture of the elements in actually as they actually look. And the reason why I wanted to show you this picture is because it kind of gives you an idea of what the periodic table is mostly made up of. When you're looking at this picture, what do you see mostly? If you said metals, you're right, because most of the periodic table is made up of metals. All of the stuff that's here on the left side of the periodic table is all pretty much metals. But it's only when we get to the right side of the periodic table that we get to the nonmetals. So we'll be talking about these main sections of the periodic table today. So elements can be categorized into 3 broad groupings: metals, those that are not metals, and those that are somewhere in between metals and nonmetals. So metals have this characteristic of having a few valence electrons, which means those are electrons that are in the outermost energy level of around the atom. And these are the electrons that are available for chemical reactions, for bonding with other elements. They have a very few number of those, which gives them a lot of their unique qualities. And as I've already mentioned, the left 2/3 of the periodic table, most of the periodic table is made up of metals. Then we have the nonmetals. These hold electrons very tightly. They usually have more valence electrons. They have 1 to 8 of them, but they have more valence electrons in general. And they usually are trying to hold on to their electrons, and they have an affinity for taking on more electrons if they can get them. So metals usually want to give up an electron or 2 or 3, whereas nonmetals want to receive 1, 2, or 3 electrons. And again, this gives nonmetals many of their qualities as well. Hydrogen, which is on the far left side of the periodic table, and then the rest of the periodic table, the right side of the periodic table, make up the nonmetals. And then you have the metalloids. That's the stuff that's somewhere in between metal and nonmetal, and it's designated for us in the stair-step line on the periodic table, which I'll show you in just a moment. This is the section of the periodic table that is made up of the elements that form the semiconductors. And this is kind of what it looks like on the periodic table. So remember I told you there's a stair-step line, and this is what you see here in green. So this stair-step green line are the metalloids, or the semiconductors. You'll see here boron, silicon, germanium, arsenic, antimony, tellurium. Those green elements here pictured are your metalloids. Everything to the left of those are the metals. So metals go this way. Sorry, it's hard to write with a mouse here. The metals. And everything to the right of that line are the non-metals. Okay? So you can notice here that the largest chunk of the periodic table is made up of metals. And these, remember, these guys here get inserted there. They're called the transition metals. So those all sit in here as well. So most of the periodic table is made up of metals. And then you have this thin line of metalloids, and then this section of nonmetals over here. So element families. Neutral elements in the same column of the periodic table have the same number of valence electrons. Each column is then called a family or a group. So this is what we mean by family or group. You pick a vertical line of the periodic table, and that is a family or a group. And a lot of times the family is known by either the number and letter above it. So in this case, this would be the 2A family, or sometimes it's known by the element that heads the family, in this case, the beryllium group. But either it's 2A group or the beryllium group. It's a vertical section of the periodic table. All elements in each section have the same number of outer electrons. Therefore, they have very similar properties to one another. What we mean by that is that everything here that's in the second column have 2 valence electrons. Everything in the first column would have 1 valence electron. If you get to the 3A group, they'll all have 3 valence electrons. So everything in the column below it has that number of valence electrons. And as a result, it gives those elements some similar properties to one another. There are 2 types of family groupings. There are the main group and the transition group. The main group is made up of the main group right here is made up of the far left of the periodic table and the far right of the periodic table. The transition group is the group that's in between that. And these represent the S and P sublevels, something you're going to learn about in chemistry class later on. I won't talk much about that here. But the number over the group equals the number of valence electrons. In other words, electrons that are available for bonding with other elements. So if we're looking here at the main group, we're talking about these sections of the periodic table. So here, the very first 2 columns, and then the last 5 columns are all part of the main group. And so this is just kind of showing a diagram with what I mean by valence electrons. If we're looking at the beryllium group, remember that was the 2A group, and we were to move down through the chart. Here we're just picturing it moving this way horizontally across, but it would be beryllium and then magnesium and then calcium and then strontium, barium, radium. So note here that in each of these cases, in the outer shell of electron, there are always 2 electrons. And that's what we mean by 2 valence electrons. These 2 electrons in the outermost energy shell are those that are responsible for bonding with other elements. And because they all have the same number of valence electrons, each of these elements, even though one has far more electrons overall, than the very first one, notice that they respond similarly as the others because they have the same number of valence electrons. Now, the alkali metals are group 1A, and it does not include hydrogen. So in the very first column, 1A, you'll often see hydrogen sitting up at the very top. But note here, when we're talking about alkali metals, we don't include hydrogen. It's considered actually a non-metal with the other side. But it kind of has metal and non-metal tendencies, so hydrogen is kind of its own class of thing. But the alkali metals are everything underneath the hydrogen. This is group 1A, which means they have one valence electron because they're in group 1A. And that one electron is easily removed, so it is very reactive. The alkali metals are extremely reactive. As a matter of fact, most of the metals that are there, you do not find them naturally like that because you'll find them in compounds with other things in nature. You have to actually go through a chemical process to remove it or isolate it from a compound because it readily combines with other things. A lot of these will readily combine even with oxygen in the air. If you have them just even present out, if they're the pure metal, you have to store them in oil because otherwise they'll react with just even oxygen in the air. If you have them out for any amount of time, it starts to tarnish and it will react with even oxygen. But they're highly reactive with water. You can even see YouTube videos of this. Take, for example, sodium, which is in the first column. Sodium on water is highly reactive. You can watch YouTube videos of some of that if you look it up. Now, the alkaline-earth metals in the second column, starting with beryllium, as we already used at that example, have two valence electrons because they're 2A. They're less reactive than the alkaline. The transition elements, which goes from 1B all the way through 8B, remember this is the transition group. The main group is the first two columns and then the last five. The transition group is the stuff in between there, and they're also called the transition metals. They all have 1 to 2 valence electrons in their outer shell. They're all metals, and few are used in their pure forms. A lot of times they're used in combination with other things. The boron family, now we're going to skip over that transition group. The boron family in the third column, 3A, has 3 valence electrons. Boron itself is a metalloid, but everything else below boron is a metal. And you kind of remember boron is actually one of the green, part of the green stair step, but then everything underneath boron is a metal. So boron itself is a metalloid. Everything underneath it are metals. There are 3 valence electrons here, because remember, in group 3A, whatever the number there is, it tells you how many valence electrons there are. The carbon family, group 4A, have 4 valence electrons, and carbon itself is part of almost all organic compounds. And as I was saying about carbon, it has almost, it's part of almost all organic compounds. And kind of serves as like the backbone structure of organic chemistry. So whenever you get into organic chemistry, carbon becomes super crucial to that discussion. The nitrogen family is in group 5A, which has 5 valence electrons, and nitrogen itself can form more chemical bonds per atom than any other family. Nitrogen often, when it combines with itself, because it is a diatomic, which means that they combine together. You don't find nitrogen by itself. It will combine with another nitrogen atom. It forms triple bonds with itself. It's one of the reasons why nitrogen is one of the things that creates a lot of energy. If you've ever heard of TNT, this N in the middle is standing for nitrogen. Use it in explosives. A lot of nitrogen components are used in explosives because whenever you break apart nitrogen in its compounds, and then when it forms together, when nitrogen finds another nitrogen and forms together, it releases a lot of energy. The oxygen family is found in group 6A. These have 6 valence electrons. Oxygen can be diatomic or triatomic. Often oxygen looks like this as a diatomic. It forms a double bond with itself. So we have the halogens, group 7A. These all have 7 valence electrons, following the pattern. They're very reactive. They want to receive or find a way to find a full shell of 8. You'll learn later on in chemistry class that the octet rule, that everything wants to get up to the number of 8. So when they have 7 valence electrons, they would love to grab one more electron to make a full outer shell of 8. These are very reactive. They exist in pure form only as diatomic molecules, and they're found in many salt compounds. So this is chlorine and fluorine and bromine and iodine. The noble gases, these are group 8A. Remember, I just told you the octet rule of having 8 valence electrons. Well, the noble gases have 8 electrons, so they have a complete set of valence electrons, which means that they exist in nature as pure monatomic gases. They don't form bonds with themselves. They rarely form bonds with anything because they're very content already. They have a full outer shell of 8 electrons. They're noble. They don't join other elements. So the group number tells you the number of valence electrons in neutral atoms of that group's elements. Elements in the B subgroup have 1 or 2 loosely held valence electrons. Remember, the B subgroup is the transition metals, that yellow section on the periodic table, and these all have roughly 1 or 2 loosely held valence electrons, and they're all metals. The intertransition elements, that's that section that sits at the very bottom of the periodic table that otherwise would be inside the periodic table, making it even wider. Those typically also have 2 valence electrons. So the horizontal rows then of the periodic table are called periods or series, and elements in the same period do not have similar properties. From left to right across a period, metallic properties decrease while non-metallic properties increase. The number of electrons in the outer level increases as we move from left to right. The period numbers are listed on the left side of the periodic table. Now, a period number tells you how many energy levels the elements in that period have in their ground state, and it equals the number of energy level containing the valence electron. Well, that brings us to section 17D, periodic trends. Now, when we're looking at the periodic table and we're considering the size of atoms as we move across and down the periodic table, we want to just kind of show some trends of the sizes of atoms. So the atomic radii increase from top to bottom. So the bigger the number of electrons and protons get, the bigger the atom. This makes sense, right? The higher the energy levels that each of these electrons get put into, the bigger the atom becomes. But as we move from left to right across the periodic table, there is a decrease in the size of the atomic radii. Why? Because just as you're adding electrons, you're also adding protons. And because there's more protons in the nucleus is trying to suck those electrons further or closer towards itself. And so as you move from left to right across the periodic table, it actually decreases the size of the atomic radius. So this is kind of a depiction of that. As we travel across or from down on the periodic table, notice that the size of each of these atomic radii are getting larger as we move down. As we move across the periodic table, we notice that each of these gets smaller as we move from left to right. So we've already talked about the distance from the nucleus that happens as we look at the periodic table. Let's now talk about the arrangement of the electrons, both in orbitals and electron dot notation. So the way you're going to learn to indicate where these valence electrons are positioned around each atom is where the X is located here on this chart. This X stands for any symbol on the periodic table. So this could be oxygen, it could be nitrogen, it could be fluorine, it could be sodium, it could be any element sitting there in for X. And then where you see these little dots around it, that's an indication of an electron. And the numbers here indicate the order in which you're going to fill these little areas around it. So if the thing only has, if it's in the 1A family, then you're only going to draw a dot in this location, and that's it. And all the rest of these would not be here. If it's in the 2A location, you would then put a second dot right here. If we get to the 3A location, you then put a third dot here. Now, up to this point, you're like, well, I'm just moving dots around. But notice here, once you get to number 4, instead of putting 4 here, you're going to put it on this side of the element. Number 5, the 5th dot, you're going to put right here. And then and only then, you're going to go back to where you have the 3, and you'll write the 6th dot, then the 7th dot, and then the 8th dot, as is shown in this diagram. So let me show you now that on another slide. So if I was asking you to show me the electron dot notation for lithium, which is in the first family, 1A family, you know that it has one valence electron. And so it would look like this if we were showing the Bohr model. But if we're just going to show dot notation, we'll just write Li, because that's its chemical symbol, and then you'll just put one dot to the right of lithium. When we get to beryllium, note here, we just put our second dot right next to the other one on the right side of beryllium. Once we get to boron, we add the third dot up here. But notice once we get to carbon, we add the 4th dot here on the left side. When we get to nitrogen, we add now 1 to the bottom. Once we get to oxygen, we come back to the top of oxygen. We add the second dot here. On fluorine, we add the next dot there. And on neon, we add the dot below neon. So notice the order in which you do these. You go first dot here, I'm sorry, second dot here, then the third dot, 4th dot, 5th dot, 6th dot, 7th dot, 8th dot. So that's how you're going to remember how to put these electron dots in as they fill. So we've looked here at the periodic table. And so the things you should remember from this lesson is these are, remember, the family groups: 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. You should remember these are the alkali metals. These are the Alkaline-Earth. This is the boron family, the carbon family, the nitrogen family, the oxygen family. Here's fluorine, which are also called the halogen family. And here are the noble gases here on the far right. Remember, everything in a column has similar properties. Everything across this way tells you the energy level in which the valence electrons are put. So in this case, as we move down the periodic table, we get into higher and higher energy levels. As you move down, the atomic radius gets larger. As you move to the right, the atomic radius gets smaller. Remember the things here on green? Remember the green ones here are called the metalloids, or the semiconductors. Everything to the left of that staircase are called the metals. Everything to the right of the staircase are called nonmetals. Well, that gives a pretty good overview of sections C and D. You've got some homework to work on tomorrow on this. And then I hope that you guys have a wonderful Good Friday and Easter Sunday. And I'll see you guys next week. Stay safe. God bless you guys.